Welcome back, dear students, to my NMR class. Today I am going to discuss about the other effects in the NMR spectra, that the spin-spin coupling. Okay, the two important factors or important parameters in connection with the NMR spectroscopy are the chemical shifts I have already discussed, and other is the spin-spin coupling. Okay, these are the two parameters that from which we get information about the structure of the molecule. So let me discuss about the spin-spin coupling, and thereby we can illustrate various NMR signal, especially first the aliphatic compound. Spin-spin coupling, that is a splitting of NMR signals. As you already mentioned, in the NMR spectra, the absorption of radio frequency by the proton, spinning proton, produce a NMR signal. Okay, we are expecting that a particular one proton can produce one NMR signal corresponding to the resonance absorption, and chemical shift says from the chemical shift or chemical shift help us to say how much distance that signal is from the standard compound TMS or standard proton TMS. Okay, that is the chemical shift. Okay, that helps that you obtain from the chemical shift. So we have a standard signal in the NMR spectra on the extreme right of the Dell scale. Okay, that is of TMS proton, and any other proton have a signal, NMR signal, that is separated from the TMS signal on the left, towards left, and the distance towards the left from the TMS signal is determined by the chemical shift the proton feel or photon felt. Okay, that is a chemical shift. But the spin-spin coupling is another interaction or another effect that results in the splitting of NMR signal. Each such a absorption signal, resonance absorption signal, gets splitted into multiplates as a result of spin-spin coupling, and that aspect is going to be discussed. Okay. The indirect interaction between the spin of neighboring magnetic nuclei that is transmitted through the intervening bonding electron is called spin-spin coupling. Suppose we have two neighboring two protons side by side, which are connected by an intervening electron cloud. Okay, then in such a cases, the indirect interaction between the spin of neighboring magnetic nuclei. Okay, so suppose that two neighboring nuclei are surely they are of spinning nuclei of resultant I spin, and if they are separated by a electronic cloud or bond, then in such a situation there is the indirect interaction between the spin of the neighboring magnetic nuclei that is transmitted through the intervening bonding electron, that is called a spin-spin coupling. Okay, so the coupling of two neighboring proton having spin through the intervening bonding electron is called the spin-spin coupling. It causes the splitting of spectral line into multiplate. Okay, that is two or more components peaks. One absorption peak is now split into two or more component peaks, that is called multiplate. The spectral line is split into multiplates. The multiplicity of a signal or peak due to a given group of equivalent protons depend on the number of protons in the adjacent group. That is very important. So the multiplicity of the peak or a signal produced by a given group of proton or a given proton depends on not the number of proton present in it, but on the number of proton on the adjacent group. The splitting reflects the environment of the absorbing proton with respect to the another nearby proton. So NMR is a very powerful that is spectroscopy or structural analytical instrument tool by which we can scan the environment of a particular proton around it. That is power. The splitting reflects the environment of the absorbing proton with respect to other nearby proton. The general rule for multiplicity. There is a general rule for multiplicity. So we can discuss one by one the general rules for multiplicity. 1. Equivalent protons with the same chemical environment do not give rise to splitting. Suppose all the protons, there are more than one proton which are in same chemical environment, they are said to be equivalent protons. So equivalent proton with the same chemical environment do not give rise to splitting, they give only one absorption peak without any splitting. Okay, all these are with respect to TMS signal. Okay, always chemical shift is there. We are discussing spin splitting in addition to the chemical shift. Then only an NMR spectrum will be completed. Okay. A signal of the PMR spectrum for a set of equivalent proton is split into n+1 component lines, where n is the number of equivalent proton in the adjacent set. This is referred to as the n+1 rule. So this is the first rule. A signal in an NMR or PMR spectrum, PMR means proton magnetic resonance spectrum, for a set of equivalent proton is split into n+1 component lines, where n is the number of equivalent proton in the adjacent set. This is referred to as the n+1 rule. So it is the number of, n is the number of equivalent proton adjacent or neighboring nuclei or neighbor. And this is referred to as n+1 rule. 3. Suppose a set of Na equivalent protons and another set of Nb equivalent protons, okay, on the left and right side of a particular proton of set Nx. Okay, suppose consider a molecule. There are ns of, consider a set of m proton or the ns equivalent protons, and there is another proton on the left and right side through the intervening electronic cloud or chemical bonding. You consider such a situation. Suppose a set of Na equivalent protons and another set of Nb equivalent protons both spin coupled with a particular set M of Ns equivalent proton. Suppose we have A, B and M as the proton sets. M is the proton set at the middle, and A are the proton set at the left, and B with the proton set at the right of M. That is the situation I am going to discuss. Okay, then the signal of the middle M proton is split into Na+1 into Nb+1 component line. This is known as the advancement of N1+1 rule. This is the second rule. So the second one rule, first is the N+1 rule, which says about the splitting, and second is the advancement of the N1+1 rule, which also says about the splitting. If there is a middle proton set, and on the left and right side of this there are another protons, then the advancement rule says that the middle proton is split into Na plus 1 into Nb plus 1 component, where Na and Nb are the number of protons on the left and right side of the particular proton. The total areas of signal does not change due to the splitting into multiplate. Even though the splitting occurs over a signal, for a particular absorption signal, the total area of the signal does not change. It remains the same. The total area of the signal is the same or does not change due to the splitting. However, the relative intensities of the multiplate are symmetric about the midpoint. The relative intensities of the multiplate are symmetric about the midpoint. Okay. The most intense line comes at the center, while the intensity going on decreases symmetrically towards the side, left and right of the central position, central point of the multiplate. The midpoint of the multiplate represents the resonance position of a group and hence its chemical shift. So, once multiplicities arise, we have to calculate, represents or calculate the chemical shift from that is the chemical shift. The midpoint of the multiplate represents the resonance position of a group and hence it gets chemical shift. Okay. So, chemical shift is represented from the TMS signal to the midpoint of the multiplate, because it is assumed that the midpoint of the multiplate represents the resonance position of a group and hence its chemical shift from the TMS. So, these are general rules for multiplicity. So, let us discuss. We will give it is with the spin coupling and chemical shift with respect to various NMR spectra, interpretation for NMR spectra of various aliphatic compound, first illustration. So, we have to make use of chemical shift and also spin-spin coupling while discussing the PMR signal spectra of various aliphatic compound and then aromatic compound. One is ethanol, that is compound CH3CH2OH, NMR signal. So, there are here three different types of proton here. Okay, one is OH proton, other is CH2 proton, and third is the CH3 proton. So, I am discussing that. A 3 proton triplet for me, they group at one point. So, first you have to look into how many different protons are there. So, there are three different protons, three different protons in the three different chemical environment is there. So, ethyl alcohol has three different chemically different proton. Okay, one is OH proton, other is the middle CH2 proton, and the next is CH3 proton. Or CH3, CH2 and OH proton are the three proton in three different chemical environment. Always on the extreme right side of the NMR signal at the point 0, delta value 0 parts ppm, there is a TMS signal is there with the highest position, which has the highest signal. So, height is very high. It is shown with much height TMS signal which correspond to the height of the peak correspond to the number of proton, which has 14 number of identical protons comes into resonance. Okay, that is why it is TMS signal is very high. Okay, these are 0 ppm. When with respect to TMS, we have to represent the three proton first in terms of the chemical shift. So, first there is a 3 proton triplet for methyl group at 1.15 delta due to the coupling with the neighboring methylene group. Okay. So, the first is CH3 group get absorbed at 1.15 delta from TMS, and it is split into 3, so it is called triplet, and splitting is due to the effect of CH2. So, CH2, 2 protons, so 2 plus 1, 3. So, the CH3 proton split it into CH3 proton signal is split into 3 lines. So a 3 proton triplet for media group at 1.15 D due to its coupling with the neighboring methylene group. Then a 2 proton octet at 3.6 delta for methylene group CH2 due to its coupling with the CH3 on the left and OH on the right. So Na plus 1 into Nb plus 1 rule, when you apply the CH2 proton, the 2 proton CH2 is split into an octet, 8 lines. Okay, due to Na plus 1 plus Nb plus 1 rule you apply, it's split into octet, and the resonance position considers the middle point, okay, middle peak is 3.6 D from TMS. Then finally the OH, a triplet for OH group 4.8 delta due to its coupling with the CH2. OH can couple with the CH2, so the number of splitting is 2 CH2, 2 proton neighboring, so 2 plus 1 3. So the OH proton, the chemical shift, it is shifted to 4.8 delta from the TMS first. You have to note, or I want to say that the NMR signal appears at a 4.2 delta. The chemical shift is 4.8 delta value 4.8 del from the TMS. Okay. So the chemical shift due to the chemical shift, OH is shifted to 4.8 delta up to absorption occurs with respect to middle signal or middle peak, and it is split into 3 due to the coupling with the CH2. Okay, look. The next is PMR signal of ethanol and CCl4 containing HCl shows some different results. CH3 triplet, there's a CH3 triplet as such, but CH2 signal is a quartet and OH signal is a mere singlet. There is a sharp difference. When you observe the PMR signal of ethanol in CCl4 containing little hydrochloric acid, a sharp difference is expected than in aqueous medium. Here, the triplet is remain as such for methyl. Okay, there is no change in the position. The triplet 1.5 delta is positioned there with the triplet, but no spin coupling between OH and CH2 proton. Therefore, the triplet, that is CH2 signal initially it is an octet, now appears as a quartet because no spin coupling between OH proton and CH2 proton. It has only coupling from CH3 only. This is explained on the basis that in the acidified ethanol, there is a rapid exchange of proton between alcohol and protonated alcohol, molecules given below, CH3CH2OH giving CH3CH2OH2 plus, which lead to no coupling between OH proton with the OH proton with the CH2 proton. So there is no chance for free proton to be there due to this exchange, and there is so the the CH2 proton is not spin coupled with the OH proton, therefore the reduce the splitting. First, maybe ask for the examination. Please study it well, or please try to understand it, the concept. Okay. The next is that explain the PMR spectrum of a diethyl ether, CH3O CH3, as the two CH3 group lie on either side of the linkage O. There is no possibility for spin coupling, and the result is a 6 proton signal singlet in the spectrum. There are 6 protons which are in the identical chemical environment. Okay. On the left and right side of the oxygen linkage, there is 3 plus 3, 6 protons in the carbon, 2 carbon, but they are in the same chemical or identical chemical environment. There is chemically equivalent protons, and also there is no chance for the coupling because oxygen will prevent the coupling at the middle, prevent the coupling. So we have a singlet for the 6 proton at a distance 3.5 delta for diethyl ether. Then next for acetone. This is also very interesting. Acetone, that is on left and right side of the carbonyl CO group, there is a CH3. Both CH3 are this. Okay, both CH3 are the chemically identical position, or they are chemically identical proton. So we can expect only one signal, and also there is no coupling because of the intervening electron cloud can't transmit this splitting because of the carbonyl group. Because the carbonyl group that prevents the spin-spin coupling or the indirect coupling between CH3, okay, through the intervening cloud, electronic cloud is not possible here. So we have only a singlet. So basically, the two CH3 groups lie on either side of the carbonyl group. There is no possibility for spin-spin splitting, and all our 6 proton are identical chemical moment, only a singlet at a 2.2 or 2.3 from the TMS. But the signal height is high, it will, because corresponding to the 6 proton intensity is very high. So height is proportional to the intensity, the ratio, the height. Okay, that is you have to look into. Then acetaldehyde or ethanol acetaldehyde. Okay, this kind of, you look here acetaldehyde, how many different proton? One a 3 proton doublet for CH3. There are 2 different types of proton, a CH3 proton and a CHO proton. A 3 proton doublet for CH3 proton due to their coupling with the aldehyde proton. A 3 proton doublet. So CH3 can produce a doublet at a distance of delta value 2.20 from TMS. So for the signal consists of, a PMR signal consists of a 3 proton doublet for CH3 due to its coupling with the aldehyde proton towards the lower del value, to a del value 2.2, the left side 2.20, and a proton quartet CHO proton, okay, aldehyde proton, CHO proton can produce aldehyde proton due to its coupling with the CH3 proton can produce a quartet at a higher delta value, at a higher chemical shift delta side, that is 9.80 ppm. So CH3 a lower delta value 2.20 ppm and it's a doublet, while the CHO proton, because of the paramagnetic or augmenting bit, I said the chemical shift, okay, or paramagnetic augmentation going to in that direction, the protonic H is present, aldehyde proton is present. So due to paramagnetic effect, it has to de-shielding, so that it produces a high chemical shift towards a low, that is delta is very high, that is 9.80 ppm, and the quartet, so a proton quartet for 1 proton quartet for aldehyde proton due to its coupling with the CH3 proton towards at a higher del value, that is 9.80. Okay. So it's a typical molecule with the, it shows a large chemical shift towards the that is del value considerably towards the left, higher del value. 6. This figure. The 2 peak have an equal intensity, while the 4 peak, the latter have a intensity. So you have to look into the peak intensity. Okay. For CH3 peak, the intensity are almost the same. 2 peak of the former are equal intensity, while the 4 peak of the latter have intensity 1:3:3:1. The absorption of the aldehyde proton is shifted towards an unnecessarily high delta value because the de-shielding produced at the aldehyde proton due to the magnetic anisotropic effect. Paramagnetic augmentation is assisting, okay, magnetic anisotropic effect I have already discussed. The next is dimethyl ether. I already discussed that. The 6 proton singlets, okay, for 3.5 something, 3.4 del value, identical chemical environment, same. Then 1,1 dibromoethane, 1,1 dibromoethane or ethylene bromide, 1,1, there is jump, dibromide, ethylene bromide, 1,1 dibromoethane. The PMR spectrum for 1,1 dibromoethane, okay, 1,1 dibromoethane, CH3CHBr2, CH3 single bond CHBr2. Here a 3 proton doublet for CH3. So two different types of proton. One is CH3 proton and another is CH proton. They are in two different chemical environment. We have first a 3 proton doublet for CH3. CH3 for CH3, that is a 3 proton. It has a doublet at a 2.255 del due to that coupling with the neighboring CH. So a 3 proton doublet for CH3 proton at 2.55 del due to its interaction spin with the CH. Then a 1 proton quartet 4. So you have a CH proton, CH is contained only 1 proton. So a 1 proton but splitting quartet is split into 4. Quartet for CH proton at 5.84 del due to its coupling with the CH3 neighboring CH3 proton, CH3 proton. So look here, TMS 0, CH3 proton, two signal of same intensity 5 del and quartet of CH at 5.8 delta 1. The next PMR spectrum of butanol. Butanol have 3 different types of proton. Okay, butanol, CH3, CH2C, double bond O CH3. So 3 different types of proton. One by one we have to discuss. Next in right side TMS at 0, delta 0. Then a 3 proton triplet at a 1.06 del for CH3 group. For the CH3 group, we have a CH3 group, we have a 3 proton triplet at 1.06 delta for the CH3 group. Splitting CH3, splitting from CH2. So neighboring is CH2, so it is 3 proton CH3 or CH3 proton signal split into 3 due to this spin coupling with the neighboring CH2. Other, a 2 proton quartet, at 2.5 delta for CH2 proton. Next comes the CH2 proton. It is split into 4. Okay, split into 4 due to its interaction with the CH3, and its position is 2.5 delta. First is a 3 proton triplet at 1.06 delta for CH3 group. Next is a 2 proton quartet for at 2.5 delta for CH2. Okay, CH2 at 2.5. Okay, that is a mistake that occurred. Second is a 3 proton singlet, at 2.14 delta for the CH3 proton. Okay, at a 2.14 delta for CH3 proton. CH3 proton is CH3. That point as C. Okay, that is at 2.14 delta for CH3 proton. That is singlet. It is not going to undergo spin coupling with any of the neighboring proton. So it produces only a singlet at a distance delta value 2.14 delta, and for proton, that is second proton, that is kind of CH2 proton, it can undergo spin coupling with the CH3 proton on the left E. So a 3 proton singlet, a 2 proton quartet at 2.5 delta for the CH2 position. Okay, it is split into 2 at a 2.5. So first CH3 1.06, then second is another CH3 on the right side of the CO group, a singlet. Next is the middle CH2, a quartet 2.5 delta value. Then ethyl bromide have 2 different types of proton, CH3 proton and CH2 proton marked as A and B. Okay, the CH3 proton about 1.5. Simply between 1 and 2 del value between from the TMS. Okay, 0. So from TMS signal it is that is first a CH3 proton that is split into a 3 proton triplet at 1.8 delta for CH3. Okay, it is due to the spin-spin coupling. Neighboring CH2 group can interact with this, so it is split into 3. While a 2 proton cortlet for CH2 group at 3.5 delta. Okay, 3.5 delta distance from TMS signal for CH2 group, the it is split into 4 due to the interaction spin-spin coupling. 3 plus 1. Okay, n plus 1 rule and as a triplet. Okay, first is a triplet and second is a CH2 is a quartet. Then is propanol. Look here, propanol, 3 different types of proton, CH3, CH2, then CHO. First CH3 get absorbed and as a triplet. So a 3 proton triplet at 1.0 delta for methyl proton due to its coupling with the CH2 proton, and another is a 2 proton octet at 2.2 delta for CH2 proton due to its coupling with the CH3 proton and CHO proton. So that it feel coupling from both sides, that is from CHO proton and CH3. Okay, so a 2 proton octet at 2.2 delta for CH2 proton due to its coupling with the CH3 and CHO, so a octet, and a 1 proton triplet at 9.8 delta for CHO due to its coupling with the CH2. Okay, the CHO shifted to a very high del value, 9.8, due to the paramagnetic augmentation effect. But it splitting occurs due to the spin coupling with the CH2, so it is a triplet. So triplet, octet, then a triplet at a much variable distance, 1, 2 point something, 2 and 9.8, that is chemical shift. Propionic acid here, propionic acid, it can be considered as CH2 proton, CH3 proton, CH2 proton and C double bond of OH. So we have 3 different types of proton represented A, B and C. First CH3 proton, a triplet, 3 proton triplet at 1.16 delta for CH3 mark A due to its coupling with the CH2. The next, a 2 proton quartet at 2.38 delta for CH2 proton mark B due to its coupling with the CH3, and there is no coupling with the COH because it is something, it is masked by C double bond OH group. So it is something we have to mediate away from. Okay. So this spin-spin coupling for CH2 only from CH3. Then a 1 proton singlet at 11.78 del for OH marked C with no coupling with the other proton. For C double bond OH, the carboxylic acid proton group proton is a singlet with a maximum chemical shift. The highest value of delta 11.7 del for the carboxylic acid proton marked C with no coupling. Okay, it's a singlet only. That's also very. Thank you very much. I hope that you have followed me. Okay.